Hey guys, Mr. Martin with the second video on Taylor series and Taylor expansions. In this video, in addition to this first example, we're going to be looking at expansions for the common series e to the x, sine x, and cosine x. All right, so first, let's do example 6 from the second page of the notes. So we have this infinitely differentiable function f of x, where f of 3 is -4. The first derivative is at 3 is 2, the second derivative at 3 is 7, and the third derivative at 3 is -5. So we're going to write a third degree polynomial centered at x equals 3. So again, let's get comfortable with this notation. So third degree is going to mean that we're doing P3 of x, right? So we're going to have P3 of x equals, so again, that's going to be f of 3 plus f prime of 3 times x minus 3 to the first plus the second derivative evaluated at 3 times x minus 3 squared over 2 factorial, which is 2, plus the third derivative evaluated at 3 times x minus 3 cubed over 3 factorial, which is 6. So you know what, actually we'll just put in 3 factorial and we'll go back and put in 2 factorial. And for good measure, let's put in 1 factorial. So if we expand this out a little further, we get, what calls part A. So then part A, we get P3 of x is f of 3 is -4. So we'll put that in focus. P of 3 is -4 plus f prime of 3 is 2 over 1 factorial is going to be 2 times x minus 3 to the first plus the second derivative evaluated at 3 is 7. So we're going to have 7 over 2 factorial, which is going to be 7 halves times x minus 3 squared plus, then the third derivative, if you see in your notes, is -5. So we're going to put -5 over 3 factorial, which is 5/6, so minus 5/6 times x minus 3 to the third power. So that takes care of part A, where we have to write a third degree Taylor polynomial centered at x equals 3. So for part B, we have to write a fourth degree Taylor polynomial centered at 0, which is going to mean a Maclaurin series because it's centered at 0. So we're going to have part B. So g of x is going to equal f of x squared plus 3. So that basically means that in this polynomial, everywhere we have an x plus, where we have an x, we're just going to substitute x squared plus 3 instead. So we're going to kind of use this to then come up with a different coefficient. So g of x equals f of x squared plus 3, which kind of implies that g of 0 is going to equal f of 3. That's going to be something that we need to keep track of. If x is 0, x squared is going to be 0 plus 3, so that again is going to be f of 3. So to do a Taylor also, and keep in mind that we were basically substituting in x squared plus 3 in here. So if I have x squared plus 3, this is going to be a quadratic the first time we substitute in x here. And then when we substitute in x where we have the squared, this square and this square are going to create the fourth degree, which is where we stop. A fourth degree Taylor polynomial does not mean that we go out to 4 terms. It means we stop when we get an exponent of degree of 4. So that is going to occur again where we have x squared plus 3 over here squared. Because if we substitute in x squared plus 3, we're going to have x squared plus 3 minus 3, which is just going to be x squared. And when we square, you know what, write it down. So in this case, if we had x squared plus 3 minus 3 squared, that's going to turn into x squared squared, which equals x to the 4th. So we only need to get to this term before we stop. So we're really only going to write at most 3 terms for our Taylor expansion. Now to do this, we still need the coefficients for our Taylor expansion. So instead of having this, so g of x is f of x squared plus 3. So basically, we can take what we know and substitute in right here. So P3 of x squared plus 3 is going to equal -4 plus 2 times x squared plus 3 minus 3 plus 7/2 x squared plus 3 minus 3 squared. And when we simplify, we get -4 plus 2x squared plus 7/2 x to the 4th, because 3 minus 3 cancels, and we're going to have x squared squared. So that's our Taylor expansion. So we get -4 plus 2x squared plus 7/2 x to the 4th, 4x squared plus 3, centered at 0. We have these common expansions for common functions. So we have like e to the x. It has the expansion 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial out to x to the n over n factorial. This term where we have this sum, this thing is called the general term. And so the general term always involves a sum, and most of the time it's a rational expression or some expression that tells you how to find any particular term of the series. So sine x, I want you to notice, is x to the first. We could write this as x to the first over 1 factorial. It is all of the odd powers, and cosine x is all of the even powers, because even the 1 is technically x to the 0 power. So sine has all of the odd powers, cosine has all of the even powers. If you remember in functions analytic geometry, we talk about how sine is an odd function and cosine is an even function. This is further proof that sine is an odd function and cosine is an even function. So for example 1, we're writing a Maclaurin series for f of x equals sine x squared, and we have to write the first 4 non-zero terms and the general term. So we're going to take sine x squared and augment it by substituting in x squared for all of the x's in this expansion. So we're going to have x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial plus, and then when we're substituting in the general term, we're going to use this where we start at n equals 0. So we're going to have the sum from n equals 0 to infinity of x squared to the 2n plus 1 over 2n plus 1 factorial. Again, this is our general term. We have 4 non-zero terms and our general term. So if we simplify this expansion, we get x squared minus x squared cubed is x to the 6th over 3 factorial is 6, then plus x squared to the 5th is x to the 10th, because we multiply the exponents, over 5 factorial is 120, and then we're going to have minus x to the 14th over 7 factorial is 5,040, plus our general term is going to equal the sum from n equals 0 to infinity of, so we multiply these exponents. This is going to be x to the 4n plus 2 over 2n plus 1 factorial. So that kind of tracks, right? So if we substitute in x equals 0, we're going to have x squared over 1 factorial, which is x squared, and so forth. So for example, 2, we want to find the derivative of the series from this previous example. So we'll kind of try to leave that in view so we can do that. So we're going to have the derivative of sine x squared is going to equal the derivative of this expansion. So there's going to be 2x minus 6x to the 5th over 6 plus 10x to the 9th over 120 minus 14x to the 13th over 5040 plus, and then we're going to still have the sum from n equals 0 to infinity. We multiply the exponent to the front, so that's going to be 4n plus 2 times x to the 4n. If we subtract 1 from this exponent, it's going to be 4n plus 1. So 4n plus 1 over 2n plus 1 factorial. If we wanted, we could simplify by having 2. Allow me to grab a calculator. So we'll have 2x minus x to the 5th plus 10 divides into both of these. So we're just going to have x to the 9th over 12 minus, I grab my calculator exactly for this one, 14 divided by 5040 as a fraction is 1 over 360. So we're going to have x to the 13th over 360 plus, I don't want to write the general term over again. This is the general term. So again, all we did was take the derivative of this expansion, which we could easily, again, verify by multiplying the exponent to the front and subtracting 1 from the exponent. In a similar way, we could, as we will see when we do example 3, we could, if we did the chain rule, end up with the derivative of sine x squared is cosine x squared, and then we multiply by 2x. And we would get the exact same expansion. So for example 3, we have to do a Maclaurin series for x cosine x. And we still want to do the same thing where we write the first 4 non-zero terms and the general term. Now cosine is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So if we have x times cosine x, that's going to equal x times, and then we're going to, again, write out this expansion. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 plus. Now, again, the general term for cosine is negative 1 to the n times x to the 2n over 2n factorial. So plus the sum from n equals 1. We want that to be 1. We want that to be 0. Excuse me. N equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. So in distributing x to this, again, we have the x, and this part is the cosine expansion. Close out our parentheses. We would get x minus x cubed over 2 plus x to the 5th over 4 factorial is 24 minus x to the 7th over 6 factorial is 720 plus dot, 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 plus the sum from n equals 0 to infinity of negative 1 to the n times So when we multiply the x, we're going to add onto the exponent, and so that's going to be x to the 2n plus 1 over 2n factorial. So, for example, 4, we are to integrate this entire series from example 3. You know what? Let's put from example 3 so that's not confusing. So from example 3. So we're going to have the integral of x cosine x, which is a problem we could solve using integration by parts. But in terms of a Taylor expansion, this is going to be easy enough, where we're going to integrate by adding 1 to the exponent, dividing by their new exponent. So we're going to have x squared over 2 minus x to the 4th. And then we have to multiply by 4 on the bottom. So 2 times 4 is going to be 8 plus x to the 6th over 6 times 24 is, I believe, 144. Minus x to the 8th over, I want to say 8 times 720 is 5760. 8 times 720, 5760. Plus plus the sum from n equals 0 to infinity. So we're going to have the -1 to the n doesn't matter. It just stays in. So we're adding 1 to the exponent. So we're going to have x to the 2n plus 2. And then we need to divide by that new exponent and multiply by 2n factorial. So 2n plus 2 times 2n factorial is our final result. All right, so guys, that concludes this video over expanding common Taylor series. Basically, all we do is take the expansion and substitute in, or in this case, multiply by the common expansion.